Hello everybody and welcome to Kaggle Basics. This is the third video in this series, and this is still doing the same housing prices data set. So let's start by going to Kaggle.com and then competitions. You go find your housing prices data set right here. We'll click that one. Go to code, and you can set the filter to most votes, and it should be the second one, this stacked regression, top 4% on the leaderboard. So that's very good predictive capabilities there. So I'll click this one here, and for me it'll be the same thing as last time. I can hit edit my copy. For you, I think you could hit copy and edit, but just click this right here, and then we will go to the code. Okay, so now let's hit the power button here, start the session, and I'm actually going to turn on the GPU accelerator for this one because it does help it to go a little bit faster. As you can see, I haven't used it at all this week, so it's no problem. If you don't have the quota space, if you've just been running a lot of code this week, then you can do it on CPU. It'll just take a little bit longer. Okay, so we'll turn that on, and these boxes here, you can actually edit these. This is what's called a Markdown box. So if you double click it, you can edit this, and you can make this whole code your own code. You can change some things and eventually get a submission. I don't think I'm going to do that in this video, but I will teach you how to submit your results in the next video. So we can change this to, you know, whatever, PW housing dataset code, and now it is your code. And when you make changes to it, you can submit if you feel like you make some kind of improvement, you could submit those to the results and get points for that on Kaggle. But like I said, I'm not going to do that in this video, but that is something you could do. For this, we're just going to keep it on tutorial mode and learn what is going on with this particular code, as it does get a little more complicated than the previous code. So shift enter. He goes over some things here. He has some links to some other codes here. You can definitely look at those. We actually did just go through this code in the previous video. And there's a bunch more. Obviously, he says the great script, imputing the features. Some of the stuff we're going to be doing in this is imputing missing values. We're going to do a better job of that. We're going to do some transforming. We're not going to do the same transformation as last time. We're going to do some label encoding and the Box-Cox transformation as well, and get dummy variables for categorical features. So let's go ahead and start. Oh, and some of the models, sklearn models here, XGBoost, Light GBM, all of the more basic sklearn models. You don't need to know the math behind them, but it is beneficial if you look at least one or two of them. But I'm not going to get into it in this video. We're just going to kind of blindly black box apply those models. So here we go. Standard first line of code here. We got import all of the different libraries that we're going to need. A couple things here, some type of warning thing, then some more inputs from the libraries, and yeah, we'll just go ahead and shift enter that, run. Now we're going to go ahead and input our training data and our test data and put them into a pandas data frame. So you can see right here, this is the data that is available on the housing prices, advanced regression techniques. You have test and train SCVs. They're about the same size. That's what this line of code is doing. If you were inputting it from your own computer, you would obviously change that to the location of the file. This is a good line of code. I'm sure most people should be familiar with it. Pull up the top 5 on the header. So you can see 5 rows, the first 5 rows, in all 81 columns. I don't think this is all 81 columns, but maybe it doesn't display them all. Yeah, it doesn't display all. This ... here indicates that it skips over quite a few, but you can kind of look at it and see. Gives a good visualization of it. Test header, the same thing. Except for one thing. The training set has the sale price. The testing set does not. So that's why when you submit your code, you submit the models that you've trained. It will run it on the test set, and that's how you get your accuracy. So as you can see, training, sale price, testing, no sale price. Pretty basic. Because if you could just train your model based on the test, it could become unfair. Okay. Now, what this line of code is doing is saying print the train data size before dropping ID is. So what we're doing here is we're going to drop the ID column. Here's the ID column: 1461, 1462. This one should be 1, 2. Oh yeah, 1, 2, 3, 4, 5. That doesn't matter. That's just an ID column, I guess. That's all it is. This number isn't going to give you any predictive capability. It's just the order in which the house is in the data set. So we're going to delete that column using this line of code here. Train.drop, test.drop, ID. So it just drops it. And what these lines of codes, this printing thing, and then it's actually calling the train.shape. All that's doing is showing the shape of this. So 1460, 81, then you drop that column and it should go down to 80. So you had 81 columns, now you have 80. For the test set, you had 80 columns, now you have 79. If I ran this line of code again, it probably would just give you an error, right? Yeah, it gives you an error because it's already been dropped. You can only run it once. You drop that, and that's that. So don't worry about this. I'm just going to keep running it and going forward. Here we go. We're doing some plotting again. We did this in the last video. We got a couple outliers. We're just going to bump those out of here right away. I remember that it was kind of complicated how I deleted them in the last one. I couldn't figure out how I did it. This one's super easy. Train.drop. If the general living area is greater than 4,000 and the sale price is less than 300,000, then you drop it. So right here, this is obviously greater than 3,000, right? Oh, sorry, greater than 4,000. So there's only 4 of them that are greater than 4,000, number 1. And only 2 of them are less than 300,000 in sale price. So these 2 get dropped. That's a much easier way to drop it than the last one. I don't remember what the last video did to drop those outliers, but this is what I'm used to seeing. That's probably how I would do it if I was going to do it. Now we plot it again, and we can see that they are now out of the data set, and we can continue on. Alright, looks like we're going to do a QQ plot again here. We're going to look at how the data distribution, the distribution of data, compares with the normal distribution, just like we did in the last video. This plot looks a little bit better because it shows the mean, which is 79, and the standard deviation, which is, or sorry, the mean is 180 and the standard deviation is 79,000. You can see a plotted normal distribution overlapping that. So again, we're seeing the skew and the kurtosis that we mentioned in the last video. And here's the QQ plot. I'm going to provide a link for a QQ plot from the University of Virginia, Understanding QQ Plots. The QQ plot, or the quantile plot, is a graphical tool to help assess if a set of data plausibly came from some theoretical distribution, such as a normal or exponential. For example, if we run a statistical analysis that assumes our dependent variable is normally distributed, we can use a normal QQ plot to check that assumption. So basically test and see if it follows a normal distribution. It's just a visual check. It's not an airtight proof, so it is somewhat subjective, but it allows us to see at a glance if our assumption is plausible, if not, and if not, how the assumption is violated and what data points contribute to that violation. So you just kind of get an idea. The closer it is to that straight line, the closer it is to a normal distribution. A QQ plot is a scatter plot by plotting two sets of quantiles against another. If both sets of quantiles came from the same distribution, we should see the plots forming a line that's roughly straight. Here's an example of a QQ plot where both sets of the quantiles came from normal distributions. Okay, so we go back. You can read all of that to get a better understanding of it. Here we have a normal distribution in red, and the scatter plot, the blue, is from our data set. It's obviously got a little bit of away from the line there, so it is not entirely a normal distribution. The target variable is right skewed, as linear models love normal distributed data. We need to transform it to make it normally distributed. So we do a log transform here, plot it, now we're much better. Okay, did that. And if you remember, that's just a log transform on the sale price. We're going to go through and do some other transformations on some other variables, not the sale price. So now the skew seems correct. Okay, so we did some of this stuff in the last video. What is this? Okay, so we're putting it all in the same data set. We're concatenating. Concatenate means combine, basically. It's just a fancy word for combine. And pd.concat means to combine, train, and test. Oh, and then we're dropping the sale price. Okay, so that means we have a total of 2,917 houses and 79 columns. Now let's look at the, oh, that's why we're doing that. We're combining all this to get rid of the missing data. So we're not going to use this for prediction or anything like that. We're going to get rid of the missing data now. All data is null dot sum divided by the length of the data. So what we're doing is we're taking all the data that has a null value that's in A and dividing that by the length of the data and multiplying it by 100. So say you had 50 NAs out of 100 total pieces of data. You would divide that, you would get 0.5, you would multiply by 100 to indicate a percentage of your data that is missing. So that's what we do, and then we're going to look at it. Boom. So this is the data that's missing in a percentage form. Pool QC, miscellaneous feature, alley, fence, fireplace, blah, blah, blah. And a percentage of data missing. 99% of the pools are missing. That's obviously because 99% of the houses in Ames, Iowa do not have pools. Alleys, maybe 80%. That means no fences, fireplaces. And in the last video, I believe that we just said, okay, delete all the missing data. Delete the pool data, delete it all, and see what you can do, because it doesn't matter. We're just learning. In this one, we're going to adapt and fill in some of the missing data and make assumptions. So we're going to go ahead and do that now. This will give us another plot here. When you see PLT, that means the plot's coming. Features and percent of missing values. So this is going to be a plot showing in a bar plot format how much of the data is missing in a percentage. So Obviously a lot of pool data here, and it kind of right here there's not much data missing at all. Out of these top 20 garage cars, it's close to 0%. I think it's probably listed right here. No, it's not. Well, basement full bath is 0.069. Basement full bath is right here, and you can see you don't even see a bar there. That's how little there is. So this just gives a better visualization. The better you get with using these tools, the better you can see your data set and examine it faster and more efficiently, and determine what the best way to do it. But ultimately, you do have to end up going through it, and that's what he does right here. And it's very clear and pretty simple what we got to do. Correlation map, we did that in the last video, so we see how it's a heat map. How well do these things correlate to each other? I explained it in the last video, so it doesn't really matter too much. Now let's get into filling in missing data, and he goes through each one here. He does a great job of explaining, hey, this data was missing. Here's what I did basically to fill in that data. So pool QC. And what I'm going to do, what you can do here is click on data description text, and you could download it using this button, and pull that up in case you need to look at anything, and it'll be right there in Notepad. So I have it right here just in case I need to look at what's going on with a specific variable if I'm trying to figure out why is this missing data here. So pool QC, obviously not pools. So all data, pool QC, fill the NAs with none. Okay, so we run that, boom, it does it. So all that means is if there's an NA in any of those pools, we're going to change it to none. So that means it doesn't have a pool. Miscellaneous features, same thing, none. Alley access, NA means no alley access, so put in a none. Data description, NA means no fence, none. Does it actually say that? Because that's one thing let's hit Control F, fence. NA means no pool. NA means no fence. Okay, so it's listed right here. That's where he's getting this from. Miscellaneous features. NA means none. So we're just changing all of these NAs to none. Not complicated, because NA has a specific meaning in this pandas data set, data frame. So when you change it to none, it's more like meaning like 0 in a way. And you'll see when we put in the dummy variables, you'll see what I'm saying there. Let's keep going here. Angle that down a little. You can see which lines of code you've ran based on this 16 here, and it even tells you the time. Okay, and how fast it went. That's pretty cool. I didn't know that. And we'll just keep running. Alley, NA, change it to none. Fence, NA, change it to none. Fireplace, NA, change it to none. And then we'll get into the more complicated ones. Group by neighborhood and fill in missing value by the median lot frontage of all. Oh, okay. So this is where we're making more of a different assumption. We're taking the median value and filling in anything that doesn't have a lot frontage and sticking in the median value for it. So how many lot frontages were missing? If this was like 50% were missing, we might consider just deleting the column, since there's an insufficient amount of data to do something like this. But if it's a very small percentage, taking the median or taking the average, it's something you can do. And you could do other things too. You could find out the value, the relationship between lot frontage and home square footage, and then predict what the missing values would be. There's a lot of things you could do here. But what we're going to do is fill in the missing lot frontage with median value. Let's scroll up and just check. Do you see lot frontage? 16%. That's a pretty good amount. But this is what he's doing. He's going to fill it in with the median, so that's fine. Good project would be to fill it in with a predicted lot frontage that based on the square footage of the house or something like that. Any way that you could get to predict that lot frontage value, and put in something there. So did I run that line yet? Let's go ahead and run that. So now all of those will be the same value, the same median value. Now, garage type, garage finish, garage qual, garage condition. Replacing missing data with none. We just did that before, so that makes sense. Garage year built, garage area, garage cars. Replacing missing data with 0, since no garage equals 0 cars in such garage. So year built would be 0. I guess that makes sense. Garage area is 0, that definitely makes sense. And number of cars that fit in the garage is 0, since there is no garage. So now we're just, instead of filling those in with none, we're filling them in with 0, which is an integer value. None is a string, which none is a categorical piece of data, which we will deal with in a little bit. Basement finish square footage. Basement finish square footage 2. I don't even remember what the difference between those two are, but it doesn't really matter. Total basement square footage, basement full bath, basement half bath. All right. We're going to put in 0 for all of these that are NA, because they all equal 0. There is 0 square footage, 0 bath, 0 half bath. It's not NA, it's 0. This is none, because these are categorical, not numerical. So you're putting in 0 for a numerical piece of data. That's what I think. I think year built, he might have messed up there. Year built, I think year built should be categorical, even though it is a number, because 0 may mess that up. But we'll keep going. We'll see if he does something to do with that later. We ran this one. We didn't run this one. Okay, so now we're filling in none for these categorical features. Now we're tackling 2 at once here. Veneer type is none. Veneer area is 0. Okay, makes sense. Categorical, numerical. Very simple. This one is different because MS zoning is the general zoning classification. If we go to right here, data description, we can see, let's go up to the top, MS zoning, you have A, C, V, I, R, RL, RP, and RM, and they all mean something different. Some of this data was missing. So NA doesn't mean that it's not zoned, right? You can't just say, no, it's none. It's zoned somewhere. You have to make an assumption here. He determines the most common zone and applies that, which is RL, residential, low density. Ames, Iowa, most zones are residential with low density. That makes sense. So we're going to fill in the most common value for that. Utilities. For this categorical feature, all records are all pub except for 1, no sewer, and 2, NAs. Since the house with no sewer is in the training set, this feature won't help in predictive modeling, so we can safely remove it. Okay, so we're going to drop that one. Oh, we dropped all of utilities. Oh, so he's saying why he dropped that piece of data. This is probably a good decision. They all are the same thing, except for 3. Right? 1 is no sewer and 2 are NA. So just delete that column, get it out of here. It's not going to help us predict anything. So that's what we do. Delete that entire column. Drop the whole column. Utilities. Boom. Gone. All data functional equals all data functional NA with typical. So functional. Let's go to see what that was. Is this in alphabetical order? No. Assume typical unless deductions are warranted. Home functionality. Okay. I guess that just means if it's screwed up, severely damaged, salvage only. So salvage only means what? You got to destroy that thing and put a new house up, and you can take out whatever you can salvage stuff inside the house. And what would minor deductions? Not a lot of description here, but that's fine. It does say assume typical unless deductions are warranted. Okay, so that's what we do. All the data that's missing, we fill in with typical. Electrical. It has 1 NA value. Most of them are circuit breaker. So put in circuit breaker. Fine. Kitchen quality, only 1 NA value again. And same as electrical, we set TA, which is the most frequent, for the missing value there. So we're just taking the most common categorical piece of data, which is TA for kitchen quality, and inputting it for the data that is not there. That way we don't have to delete an entire column, which is pretty good data. Again, exterior 1 and 2 only have 1 missing value. We can substitute with the most common string. Which I guess was this 0 here. We're filling it with this mode the first answer for exterior first and exterior second. So let's go to exterior. I should probably just control F that. Exterior. Did I spell that wrong? Oh. Okay, fine. Exterior first. Sorry if this writing's a little small. I guess this is the most common value. Asbestos shingles, and asbestos shingles is the same for the second one as well. Okay. So we're filling in those two. Since only one's missing, it's not a big deal to do that. Sale type, fill in the most frequent, which is WD. We're not even going to look at what that is. And now this line of code is MS subclass, which likely means no building class, which means you can just replace it with none. And now, is there anything else missing in this data set? Can we start applying models directly to our data set after we encode our variables? If we have missing data, we have to tackle it. If we don't, then we're good to go. And missing No missing data. If we scroll back up, when we ran that line of code before, all of this popped up, missing ratio. So this is the same piece of code. Control C. Same line of code that we just ran before. Only this means put, I don't know, whatever the standard amount is. I don't think it would be all of them, but I think it's like 5. I think header normally means 5. But if you put in 10, it'll specifically be 10. Maybe it's only the first line. I don't know. But regardless, there are none. So we can delete that. We can run it again just to make sure. You put a 5 in there, it doesn't matter. There's nothing there. There's no missing values left. So now I'm going to include this in the video description as well. We have transforming some numerical variables that are really categorical. Sorry, this first let me explain this and then I'll talk about transforming categorical data to numerical data, or how to organize it as numerical data, which is called encoding, label encoding. It's just right here. It's the next line of code. But first, let's talk about this. These pieces of data are categorical pieces of data which are organized in a numerical way, if that makes sense. MS subclass, overall condition, year sold, month sold. This is all categorical data. Month sold is you could attribute a number to it, but it's better to attribute it to a category. MS subclass is the most easy to understand example of this. Let's go to our data description. Let's go to MS subclass. It's either 20, 30, 40. Sorry if my video just froze there. It's either 20, 30, 40, 45, 50. All of these different numbers here are indicative of which type of dwelling is involved of the sale. So although it is organized in a numerical fashion, from 20 to 190 in intervals of 10, it is actually describing a categorical piece of data, whether it's one story, 1946 or newer. So how do we deal with that? You change it to a string. So a string is, you can kind of think of it like as a word. I think I did Google it here. String, Python. What is a string in Python? A string is a collection of alphabets, words, or other characters. So in this case, it's going to be or other characters. It's going to be numbers. We're changing it from telling the computer like, hey, although this is a number, treat it as if it was just a word. It is one of the primitive data structures and are the building blocks for data manipulation. Python has a built-in string class named str. Strings are immutable, which means they cannot be changed after they are created. Okay. Fair enough. Apply str. We're changing it to a string. Same with overall condition, same with year sold, month sold. Although these are numbers, they're not numbers anymore. They're not integers, they're strings. Did I even run that? Nope, so I'll run that now. Shift enter. Continue moving on to label encoding. So I'm going to include this in the video description as well, which is this. He chose label encoding. There's something that most people use, which is called one-hot encoder. Here's a quick article on it. I feel like, and I might be wrong in this, in almost all cases you should use one-hot encoder, but he does use label encoder, which I guess is fine too. Which label encoder essentially changes the country here, which is the categorical data, to a number. 0, 1, 2, 3, 1. The US is 1. So that kind of unbalances it, because you can't say like the country 4 is, India, in country 1 is US, you can't say, okay, so India equals 4 times US. It doesn't work that way. So that's why a lot of people use the one-hot encoding method, which gives it an entire column. Like, is this country Japan? 1 equals yes, 0 equals no. So it gets a whole column. Is the country US? These two are. The rest of them are 0. Is the country India? So it just changes it all to ones and zeros, it works better. But he does it this way. He's probably smarter than me, so I think he must have done it for a reason. I just don't know what that might be, or what effect it has leaving it as a label encoder and not going to one hot encoder. But we'll do that. So now what this does, we import label encoder. So here's all the columns, and then you apply label encoder, and this line of code will directly transform that data into numerical data. So there's the shape of all the data, of all of our data. Yeah, this is all the houses and the 78 variables. Now we're down to 78 because we dropped another column earlier. We were at 79 and we dropped probably not important, but let's see what it was. Utilities, right? Dropped it. So when we did that, we went down to 78 columns of data. All right, keep it on. He creates his own variable here, which is fine. It makes sense. I don't know if it was necessary to do it, but of course when you're looking at a house, you see this variable. So I'll just explain what it is real quick. Total square footage equals total basement square footage plus first floor square footage plus second floor square footage. So now you have one variable which indicates the total amount of square footage, and that is one of the first things you look at when you buy a house, so it does make sense. But I don't know if from a modeling perspective if you needed that, because all this data is there. But fine, we got another column. We're almost done here. Numeric features, all data types equals object. So now we're going to look at how skewed our data is compared to a normal distribution. A lot of skew here in a lot of these. And what we're going to do is apply, just like we applied the logarithmic transformation, we're going to apply the Box-Cox transformation. To all of them that have a skewness of greater than 0.75, which this guy's code is very nice. It literally prints this out for us, how many there were. There are 59 skewed numerical features that will have the Box-Cox transformation applied to them. Okay, so we did it. We transformed all of those. That's how easy that was. Transformed all of those data that did not have a very nice normal distribution. They had a lot of skew in them, and now they are much more closer to a normal distribution. And you can just do that. That's how easy it is. Now we're going to get dummies. What does get dummies mean? Convert categorical variable into dummy indicator variable. So maybe this ends up making it more like a one-hot encoder. I don't know. Because now we get these dummy variables for all of the data. Yeah, that is what it did. Because now you can see how many columns we have here. So all of that categorical data that was organized in a 0, 1, 2, 3, 4 fashion now gets organized into the one hot encoder fashion. So I guess label encoder plus get dummies will equate to one hot encoder. I don't know. I'll read through that. Either way, that's okay. Training and testing. Number of training. So we're taking all the data and we're dividing it between in train. If I said Control F in train, it's the initial shape of the training. So it's like, I don't think we ever saw exactly how many it was, did we? Doesn't matter. It's like 1400 or something like that. Like half of that, half of 2900, which is close to 1400. So we do that. All the data that is, let me X out of that. All the data that is after up to in train is in the training set, and because we just concatenated those earlier where we stacked them on top of each other, so we're just splitting it back apart into a training and a testing. Now we do the modeling portion of this, which hopefully this doesn't take a long time to run. If it does, then I don't know, maybe I'll explain it in the next video. I still have it on GPU. I ran it on CPU and it took a while before this video. Quickly, let me explain what these models are. You have sklearn, linear models, you know, the elastic net, lasso, Bayesian ridge. I know what some of these are. I know what the elastic net is. Random forest regressor, I know what that is. Some of them, I don't know what they are, but I still have used them. I've still hit this line of code, which is, actually this line of code isn't applying it, but this line of code is. That's all it takes to apply the lasso model on our data set and predict sale price. That's it. So it's very simple. Just because you don't know what's in the lasso model doesn't mean you can't use it. Because a lot of people just use a bunch of models and then take the average, which is what we're going to do anyway. So it is beneficial to learn what one or two of these are, but you don't need to go and learn the exact math of each one of these linear models. Okay, so let's keep going. What this one does, RMSLE, which is root mean square something something. Root mean square logarithmic error. This is a way to describe how accurate our models are. Lasso, let's run it. eNet, elastic net, let's run it. Kernel ridge, run it. Gradient boosting regressor, run it. I mean, see all these variables that you need in here. You could change it too. See if you get, it's your own model at that point. If you change this to 0.1, or if you run it 10 times from 0.1 to from 0.01 to 0.1 and determine which one's the best and use that for your model. Now let's do this one too. Speed regressor. So we're running a bunch of models. We don't know what all of them are. And now this RMSLE underscore CV will print the score that we got. 0.11, 0.11, 0.11, pretty close. Pretty close. I'm gonna keep running it. If it doesn't finish in time, I don't want to have you guys wait on this video just to see. Run it, run it, run it, run it. I'll just run the rest of the code. And we'll see what finishes and what doesn't. Looks like a lot of stuff, but we're basically at the end of it. Okay. So let's go back up and see if that finished. No, this is the one that took a while on the last one too. But basically what the rest of this code is going to do is... it looks like it finished, but it's still going. That's a little strange. We run all these different models, right? The lasso, the eNet, the KRR, kernel ridge, gradient boosting, and all of these. And now you can see the scores coming in now. They're all around the same, 0.11, 0.11, you know, with the third digit is changed on some of them, 0.116. But they're all pretty close in accuracy. So now what we're going to do is kind of make a hyper model where we take all 5 of these models that we just had and take the average of them and create like a mega model which incorporates all of them and predicts based off of that. And that's what this code that's running right now will do. And this is a very simple stacking method that he uses here. Averaging base models, that's all it's called. And we use all 4 of those. What score do we get? Look, it went down from 0.11 to 0.109, which doesn't seem like a lot, but in the world of prediction, every percentage point counts. So it is a lot. So we improved our predictive capability by averaging these 4 models together. And it says, wow, it seems even the simplest stacking approach really improved the score. This encourages us to go further and explore a less simple stacking approach. So I don't want to get too far into how this works, but to somewhat basically describe it, it takes which models are better at predicting certain things and using those models, and it's more in depth, and I guess it's called a meta model. You can read all of this and learn a little bit more about it. And this is where he gets in the top 4% of scores, which is very good. That's very good. Boom. So in the end, he ends up using stacked prediction plus XGB gradient boosting prediction plus LGB prediction. In order to obtain the best model. So it's not really too important how much better it gets. I think it does get closer to 0.1 for the RMSLE error. And in the next video, it does print out a sub to SCV submission SCV, which you could take and submit and get points for. Or you could edit the code a little bit and try to improve it and submit it and then get in the top 3%. So I'll show how to do that in the next video, and we'll also tackle a new data set and get out of the housing prices data set. So I think that's it for today. Thank you for watching, and I'll see you in the next video.